Okay, so in the last lecture, we considered some more of the structural aspects of the Standard Model, in particular the symmetry structures and the approximate and accidental symmetries, some of the approximate and accidental symmetries that show up in the Standard Model at low energies. However, it's now time to really start to get into the nitty-gritty and some details. And normally, as I mentioned before, one might be tempted to take a sort of historical approach and build things up as they develop. So for instance, the lepton sector and U1 electromagnetism, electroweak theory, and then QCD. But I'm really trying to take more of a top-down look at the Standard Model. And one thing that really is the sort of the keystone of many aspects of the Standard Model, be it electroweak symmetry breaking or fermion mass generation, which is of course related, is the Higgs sector. And so I believe actually from a sort of pedagogical view, it's perhaps better to discuss the Higgs sector first before we go on to discuss, in my mind, more complicated topics like QCD, even in any detail. And so today I want to discuss the Higgs sector, and I want to discuss spontaneous symmetry breaking from a more general perspective. First of all, considering spontaneous breaking of global symmetries, and then the spontaneous breaking of gauge symmetries. And then we will go to the fully fledged form of that in terms of the Standard Model. Now, spontaneous symmetry breaking is a topic that you will all be familiar with, whether you know it or not. If you have played with magnets, for instance, magnets at high temperatures don't really have any magnetism because all of the spins in the magnet are pointing in different ways. But once you cool the magnet, all of the spins will pick a direction and point in the same direction. And that's what creates the magnetism. And that is a form of spontaneous symmetry breaking at high temperatures. The material is essentially homogeneous. There's no preferred direction. The spins are all pointing all over the place. So on average, they're not pointing in a preferred direction. Yet once you cool down, it picks out a preferred direction and spontaneously breaks some space-time symmetries. This is also something that occurs in superconductors. It's something that occurs to some extent even when liquids are cooling or gases are condensing into liquids and so on. So spontaneous symmetry breaking is everywhere. It's to a large extent, not entirely, but to a large extent, anywhere that you see a phase transition, where a phase transition might be, the boiling of water or something like that, or even more mathematically worded as I think Ehrenfest classified, when some of the first or second or higher order derivatives of some properties of material, some order parameter, we would normally call it, become discontinuous. When we have a phase transition, often that is associated with some form of symmetry breaking. And so symmetry breaking and spontaneous symmetry breaking are very ubiquitous, and so I think this is a very rich topic. It is not just limited to the Standard Model. So when I go through these topics, please bear in mind that what I'm saying has very, very broad applicability. The Standard Model is an example of it, but it's actually an example that also happens to be extremely similar to superconductors, for instance. They're really, the differences are very minor. Okay, in terms of symmetry structure. Okay, so let's go on and discuss the Higgs sector. Spontaneous symmetry breaking. So what we're going to do is consider a model that we've already discussed a number of times, and this is a model with a complex scalar field which has some charge under a global symmetry. So this would be, for instance, the U1 symmetry that you've heard me going on and on about for quite some time now. So we'll start with our U1 symmetry and the complex scalar field phi. And the U1 symmetry will act on phi by rotating it, as I've said many times now, unfortunately, by a constant phase here. This would be theta. And so you know this well. And what I'm going to do is I'm going to write a theory that has, a theory being a Lagrangian, so an equation that makes predictions, that has this symmetry, but which will spontaneously break the symmetry. So the Lagrangian is the following. The kinetic terms, which you've seen many a time, now. And then I'm going to write the mass term and the a quartic interaction. So this is going up to all the terms we can write consistent with the symmetry up to dimension 4. I'm going to write them in a slightly suggestive manner by writing them like this. So lambda is some parameter. It's has dimensions of coupling squared, and f is a number. It's like a decay constant. So we can expand this out if we wish. It's the exact same thing. We would have the kinetic terms which look like this: d mu phi squared. By d mu squared, I mean d mu lower index phi dagger contracted with d mu upper index phi. It's just sloppy notation, but it's useful notation. Expanding this out, we'll get a mass term that looks like lambda f squared over 2 phi squared minus lambda over 4 phi squared. Actually, that should be over 4, shouldn't it? Over 4. And then some constant, which will go like lambda f squared over f to the 4 over 16. So this constant is unimportant. In a quantum field theory that doesn't involve gravity, this can just be, this has no physical effects. We can ignore that. This term here looks like a mass term, but as you saw in your QFT lectures, the Lagrangian looks like kinetic energy. This is very heuristically, kinetic energy minus potential energy. So the potential is minus this object here. So we see we have a positive quartic because we have a minus sign. So we've got a positive quartic in the potential, but a negative mass squared. I prefer, to a great extent, to write it in terms in this sort of term here, because you can see that automatically, because this is squared, it's positive definite. So the minimum of the potential will be whenever the expectation value of this guy is equal to that guy. Okay, so now let's plot this potential. So if f squared is positive, so f is a real number in terms of this potential here, then we see that the minimum is not at phi equals 0. The minimum will actually be away from phi equals 0. So I'm going to attempt to badly draw the form of the potential. So it would look like this. This is already messed it up. This is the axis about which phi equals 0. This is the potential energy, so we're calling this, the potential is minus this object here. And you see that there's sort of contours like this of constant energy. And we see that this point here, and it's also, so we're rotating. So if we were to parameterize phi as a complex number in terms of something like r e to the I theta or I omega, where omega is an angle, then omega would be the direction where you're rotating around this axis. Okay. Or if you wrote it as, phi is x plus iy, then this would be the x direction, that would be the y direction. But I think it's simpler to understand in angular coordinates. So this axis here is sort of the modulus. So this is the sort of magnitude of phi, because this potential only depends on the magnitude of phi. It doesn't depend on the angle. And we see here that the scalar field does not want to sit up here. That's an unstable maximum. It would fall down. It would roll down all the way to here, where it is happy to sit. That is a true local minimum. Okay. Now, if we look at this from a local perspective, so imagine we would just put the scalar field down here and give it a little kick. Then one can ask, well, what happens? So suppose we kick it in the radial direction. So we kick it, say, this way. What will happen? Well, it will oscillate up and down at some frequency. And to a good approximation, if we were to Taylor expand about this point here, that frequency is actually just corresponds to the mass of the particle. So the mass of this degree of freedom, as we call it, this direction here, which is the radial direction. However, what would happen if we kicked it into the board, if we kicked it in this direction here? Well, if we kicked in that direction, here, we would see that what would happen is that if we look from above, so let me draw this, expand this out. If we look from above, what would happen is that it would just roll around the this local minimum. This is like a Mexican hat shape, and it will just roll around that local minimum. And all the points around that minimum, that minimum of the Mexican hat, have exactly the same energy. So it doesn't cost you any energy whatsoever to kick it in that direction. Whereas if you want to kick it in this direction, you want to get it to move uphill a little bit, that's going to cost you some energy, and that's essentially related to the mass. So we see that there are sort of, we can already, without doing any or much in the way of equations, we can already tell that there are two things that can happen. So it's a complex scalar field. So there are 2 degrees of freedom, as we call it, and those are basically fields. If it were a single real scalar field, that would be 1 degree of freedom, but it's a complex scalar field. So there's 2 pieces, the real part and the imaginary part, and they can vary separately. Equivalently, we can consider that to be the radial component and the angular component, and they can vary separately. And we see that one of them, the radial component, will be massive. So we expect to see a massive particle in this theory. But the angular coordinate is not massive. It doesn't cost any energy whatsoever to move it around in the field in the angular direction. And this is a very, very important fact, and it's a very, very deep one. So we're only seeing it in terms of this model here, but actually this manifestation of a massless degree of freedom, a massless particle or field, is something that is intimately tied to the ideas of spontaneous symmetry breaking. So in a second, we're going to calculate the masses of these particles and see how this works by playing with the equations a little bit. But what we can see here in terms of symmetries is very interesting. So this theory, the thing that we wrote down, the actual Lagrangian itself, respects this global symmetry. We can do a U1 transformation in the field, and this Lagrangian remains unchanged. So this means that all of the physics respects the symmetry. If we do a U1 transformation on phi, the Lagrangian remains the same, and in this case, the path integral even remains the same. Okay, so the theory respects the symmetry. However, when we go to the ground state, which we call, often call the vacuum state, when we go to the ground state, phi does not want to sit here at all. It actually wants to sit out here. So suppose we put it at some point. We can pick any point we want that's along this minimum. So let's choose it at the point, x equals this distance here, and y is 0. So say we set it there. That point itself does not respect the symmetry. If we do a U1, if phi has taken some constant value in the vacuum, and we do a U1 transformation, the Lagrangian does not remain the same anymore. So something's happened to the symmetry, and what we say is that the symmetry has been spontaneously broken, because the theory respects the symmetry, but the ground state, the vacuum, does not respect the symmetry. In some sense, the terminology of spontaneously broken is a little bit misleading, because actually the symmetry is still there, and that's why you get a massless field, as we will see in a second. What we say, though, is that in this picture, the symmetry is linearly realized, because you just multiply by a phase, and so the object phi transforms in the usual way under the symmetry. Whereas we say that in the vacuum, the symmetry is there, but it's non-linearly realized, and so the way we see it manifesting itself in terms of the fields is very different. So let's go ahead and see that now that I fleshed it out a little bit more. Okay, so I don't really want to wipe off that. Okay, I'll work over here. I don't really want to wipe off that picture because I think the picture is more useful than the equations, to my mind. But let's carry on and study what the mass of these particles will be. So I'm going to pick a parameterization. You can choose to parameterize your fields however you wish. It's a quantum field theory, and that's one of the freedoms you have. We call it like reparameterization invariance. Essentially, it's sort of like a redundancy of how you describe things. So long as you parameterize it in terms of the right number of variables, then you can't really go wrong. And for this situation here, I think the smartest parameterization is of our complex scalar field, so it's a function of the space-time coordinates, is the following. F plus rho of x over square root of 2 and then multiplying e to the I g of x over f. Okay, so so what have we done here? So f is a constant, and if you recall, that potential was just phi squared minus f squared over 2. So if rho was 0, then we'd exactly minimize the potential. So rho is like the perturbation away from that local minimum. So rho is the field that now fluctuates in this direction here about this local minimum. And what is G? So I'm calling it G suggestively. You probably already anticipated that stands for Goldstone boson. So G is the angular direction. So G is the field that corresponds to going around this potential around the bottom of the Mexican hat potential. Okay, so now we'll just plug that straight into the Lagrangian that I've written down. I'm not going to write it down again. And we'll plug it in and we'll see precisely what we get. When we do that, we get the following Lagrangian. We get Lagrangian is equal to 1/2 d mu rho. I'm being sloppy. This is d mu rho plus 1/2 d mu g. These are both squared. That is multiplied by f plus rho squared over f squared. So this is not, it says this is not a canonical kinetic term. The kinetic term here is now multiplied by a function of the other fields, which is sort of interesting. Lambda f squared over 2 rho squared minus lambda over 2 root 2 f rho cubed minus lambda over 8 rho 4. I wouldn't be surprised if you follow through the calculation that I've made a factor 2 error in any of these coefficients, then you'd be experiencing the same attention to detail that all of my collaborators get to enjoy the pleasure of. So I'm sure there are mistakes. And what do we see here? So here are kinetic terms. And here is the scalar potential. And the scalar potential is entirely independent of G. And so this is super, super interesting. G interacts with rho here, but it has no scalar potential. And in fact, rho has mass. So the mass squared of rho is lambda f squared. It has a trilinear interaction. Any of you who started studying Higgs physics already will be familiar with the importance of this at the LHC. And a quartic interaction. So we have a massless scalar field, which is G, and we have a massive scalar field, which is rho. Now you may ask, and I sort of have been tempting you to ask, where has the symmetry gone? And the answer is sort of nowhere. This is why I feel like spontaneous symmetry breaking is a little bit of a misnomer, because these things get hidden in other places. And what we would say, as I mentioned, is that it's non-linearly realized. So before, the action of the symmetry was that phi would go to e to the I theta phi. And we say that this is linearly realized. But after, the symmetry acts in the following way. Rho goes to rho, nothing happens. But G goes to G plus theta F. We said this is non-linearly realized. Now what do I mean by theta goes to theta plus, sorry, G goes to G plus theta F? I literally mean that you're just shifting G by a constant. So if we stare through this Lagrangian, there's no G, no G, no G, no G, only a G here. Now suppose we shift G by a constant, what happens? Well, you get d mu of G all squared. When the d mu hits a constant, it just gets nothing. When you differentiate a constant, you get 0. All right, do you remember that from high school? So when d mu hits G and you shift it by a constant, you get 0. So all you get left over is the d mu hitting this part of G, which is just what you had in the first place. So the theory actually remains the same. So even though the symmetry's been spontaneously broken, there's still a remnant of it there. And that remnant in this case is a shift symmetry for G. And that's a really, really actually deep and profound thing. And it's it's something that shows up when continuous symmetries are broken everywhere. So it relates to many different scenarios, and we call that. That's why we call it a Goldstone boson, because Goldstone proved that as a general theorem, that when you have continuous global symmetry like this that is spontaneously broken, you will have massless scalar fields who have some form of a shift symmetry. By the way, I said that like there were two conditions, but they're both the same condition, because there's no way to write a mass term for G without breaking the shift symmetry. So if there is a shift symmetry, that implies that it's massless if it was an exact continuous symmetry that was broken. I'm going to write this up because I think it's important for you to be familiar with this, although I assume you've probably heard of it a few times before. So Goldstone's theorem. Essentially, for every spontaneously broken continuous global symmetry, you get a massless boson. It's essentially, it's more involved than that. It's for every generator. Remember, I discussed that for SU2 there were 3 generators, which are the 3 things that can parameterize any unitary 2x2 matrix. For SU3 there are 8. It really is that there's a massless Goldstone boson for every generator that's broken. So every generator which does not annihilate the vacuum, but this will do for us. You get a massless scalar. I believe, I'm not sure, so you can fact check this, but I believe Goldstone proved this while he was at CERN here. I think it's a CERN affiliation on the paper. Okay, and it's also sometimes called a Nambu-Goldstone boson because Nambu did very much related and overlapping work at the same time. And this is a very general theorem. Of course, when you break some additional space-time symmetries, the story gets complicated. But if it's a purely internal symmetry, like one of these global symmetry here, then you get one of these fields. Okay, so that is spontaneous symmetry breaking for a global symmetry. Now, one might ask, what happens if it's a gauge symmetry? And now we're starting to get more involved, and we're moving towards Higgs physics. So let's study spontaneously broken gauge symmetries. At this point of a lecture, I would usually ask you if you have any questions, but that's not possible now. So if you have any questions at this point of when you're watching the lecture, then please feel free to drop me a line and get in touch, and I'd be very happy to answer them. Okay. Spontaneously broken gauge symmetries. Okay, so now we want to promote this global symmetry to a full-blown gauge symmetry. And we saw how to do that even, I think, in the first lecture. So what we do is if we want to make that symmetry transformation parameter, for this case a U1 symmetry, it's a phase. If we want to make that a local variable, a field which can depend on space-time position, then we can't just plug that in straight away to that old Lagrangian and get an invariant theory. We have to introduce a gauge field. It's absolutely obligatory. There's no way of making it a local symmetry without doing that. And we saw how to do that. And we introduced the gauge field, and we saw the field strength tensor and the kinetic terms for the gauge field. So let's do that again. But this time what we're going to do is we're going to spontaneously break the symmetry and see what happens. So we saw that the Lagrangian in this case was -1/4 f mu nu plus big D mu phi all square, where big D mu was this here. D mu was D mu plus I G A mu. And then we have, sorry, minus lambda over 4, and then the same thing again, phi squared minus f squared over 2 all squared. So this is exactly the same scaling potential. The only thing that's changed is we've promoted this now to being a local symmetry. So now phi goes to e to the I theta phi, where theta is a function of the space-time coordinates. And in order to tolerate that, in the derivative, we can't just have the derivative because that would pull out derivatives of the transformation parameter of theta. We have to introduce a compensating gauge field, and this time I think it's the first time I've done it. I've introduced the gauge coupling. In previous lectures, I was setting that to 1 just to make it a little bit more simple. But I introduced this gauge field, and the gauge field transforms like mu goes to mu minus d mu of theta over g, for instance, and then all that dependence will cancel in there. So this whole thing remains invariant, but also this term here is invariant under that symmetry as well. Okay, so let's do the same old thing, and we will parameterize. I'll just write it in a slightly different color to make it more clearer. We will parameterize it in the same way. So what do we have? We have phi was equal to f plus rho over root 2, where rho is a space-time field, e to the I g over f, where g is a space-time field as well. Okay, so now the Lagrangian that we have gone to the bottom of that Mexican hat potential, to that local minimum, looks like this. So we've got the same sort of terms, nothing has changed in this gauge sector, f mu, f mu, u. From the kinetic terms, we will get the terms we saw before, d mu rho squared plus 1/2 d mu g squared f plus rho over f squared all squared plus lambda over 4 root 2 f rho plus rho squared over 2 squared. So all of these terms are the same as we saw before, and when we expand this thing out here, we get exactly what we saw before. But what has changed is that now we get, I'll do it in a different color again, we get 2 new terms that involve the gauge field. They go like g squared over 2 rho plus f squared mu mu, and g rho plus f squared over f a mu d mu g. Okay, so we just plugged this in. We've gone to that local minimum in the potential. But now, because everything remains the same as before, except now we have gauge fields, and just from these covariant derivative terms alone, we picked up 2 extra pieces. One is where we're expanding about the phi minimum, which is rho plus f, and then we get 2 factors of gauge fields. So we get a g squared and an mu, so you get something like that. Now, when we have 2 fields in a term in the Lagrangian and no derivatives, that's not a kinetic term, that's a mass term. So what we see we've generated here is actually a mass, a 2-point function for, sorry, not a 2-point function, a 2-point vertex for the gauge fields. And also this weird term, which is like a kinetic term because there's a derivative on the gauge, on the Goldstone boson, but it's also got the gauge field. So this is a bit of a funny term. Now, as it stands, it's sort of a bit tricky to extract the physical implications of these extra terms, but we have the gauge invariance of these terms and this term, and so we are at liberty, if we wish, to make one last gauge transformation. It's not going to change the physics because the gauge symmetry, after all, was just a redundancy, so we can pick any gauge we want. And we can pick a gauge where we go from this setup here to doing one last transformation, which is that this last transformation will be that a mu goes to a mu minus d mu g over little g f. And when we do that, something really remarkable happens. G completely disappears from the Lagrangian. Right, we're at liberty to do this. We can always do a gauge transformation on the gauge field where it changes up to the derivative of some space-time field. That was initially theta, but we can do it for anything we want. And if we make this choice here, then something remarkable happens, which is the gauge field vanishes, and the final Lagrangian is the following. Now, this is just picking a gauge. So you can pick different gauges and you will get theories that look different, but are actually physically identical. But for our purposes, this gauge is a very useful one because it, in terms of the Lagrangian at least, it really exposes what's going on here. Sort of what we call the Higgs mechanism. Okay, so this is the final Lagrangian. What we see here, in this gauge, what we see here is that this is essentially what we would normally refer to as the Higgs boson. It's the Higgs boson of this theory. It's the massive scalar field that you get whenever you write down a sort of nice, simple perturbative model of gauge symmetry, spontaneous gauge symmetry breaking like this. And here we get a prediction for the Higgs mass from expanding this term here out. But here we have something super interesting. We've got when rho is 0, so we're just really sat at the minimum there, where f is just some constant, which is tells you that it's just set by the distance out to the minimum of the Mexican hat potential. We've got a mass term for the gauge bosons. And then here we've got an interaction, when we expand this out, an interaction between the Higgs and the gauge bosons. Higgs gauge interactions. Now you might ask, where has this non-linear symmetry gone? Because in the global case, whenever we went to whenever we spontaneously broke the symmetry and went to the vacuum, we found that there was actually, the symmetry was hiding somewhere, because you could always perform this shift symmetry on the Goldstone boson, and that rotated it around the bottom of the potential. So what's going on here? Here, that non-linear symmetry is actually still there, or a gauge version of that symmetry is still there, where we can still actually shift the Goldstone boson, but now it's a local symmetry, so we now do a shift symmetry on the Goldstone boson, so it goes like G goes to G plus theta of X, for instance, and at the same time do a compensating shift on the gauge field, where this would be d mu of theta of X. And the theory remains invariant. So there's actually also, there's a non-linear version of this story that's hidden in here as well in the vacuum. Now, this thing about the Goldstone boson vanishing is for me, I think, super interesting and compelling. It's one of the sort of things that got me excited when I learned about this mechanism. And you may have heard sometimes it's said that the gauge field, when you spontaneously break a gauge symmetry, the gauge field eats the Goldstone boson. And that's what has really happened here. Because when we started off with this theory, we had a massless gauge field, nu. Now, a massless gauge field, like most massless fields, only has two polarizations. It can be pointing along, the spin can be pointing, well, not along. For example, if the photon's traveling in this direction, the spin could be, for instance, pointed up or across. There's only two different degrees of freedom there. There's various ways of arriving at that. There's four components in the gauge field, right? Because it's a vector, but actually a massless representation, a massless spin-1 representation of the Poincare group only has 2 degrees of freedom. You can understand that essentially as being related to the freedom to do field redefinitions and the gauge symmetry, essentially, or Lorentz symmetry and the gauge symmetry. However, there were 2 degrees of freedom in this complex scalar field, right? There was the real part and the imaginary part. So in total, we have 4 degrees of freedom. In this theory, we've got rho, which is 1 degree of freedom. And we have a mu, which is the gauge field, but now it's a massive gauge field. Now, a massive spin 1 field has 3 degrees of freedom, because you can the spin can essentially be polarized not only orthogonal to the direction of travel, but also along the direction of travel. So we've got 3 degrees of freedom here and 3 degrees of freedom here. So in some sense, we could never have had the Goldstone boson as an extra degree of freedom in any case, because the number of degrees of freedom remains the same. The number of total fields in the theory remains the same. So we've got 4 here and 4 here. And what has happened is that the Goldstone boson has become that extra spin, in some sense, that extra degree of freedom that allows the spin to point along the direction of travel. And so, even if we were to not do this transformation to get rid of the Goldstone boson, we would never see it as a separate massless entity, because there could only ever be 4 degrees of freedom in total. So if we work in a different gauge where we explicitly keep this Goldstone boson, still what we would find if we were to do scattering experiments and study this thing would be a massive spin 1 field and a massive scalar rho, and that would be it. Okay. And that's essentially the bare bones of the Higgs mechanism. Now, this was developed in the context of superconductivity for abelian theories that are not Lorentz invariant, even in advance of the Higgs mechanism. But then, really, I would say the whole cohort would be Anderson, Kibble, Goralnik, Brout, Engler, and Higgs. All pieced together at various times, and Higgs is famous for pointing out that this guy remains in the theory, and put together various different extensions of that were Lorentz invariant and abelian, and then later on non-abelian for non-abelian symmetries as well. And that is why this degree of freedom, rho, which we sometimes call the radial mode, because it's like the mode that points outwards from the axes, is known as the Higgs boson. Okay, so what are the predictions here? So there's some really extraordinary things about this, where the symmetry, the gauge symmetry, puts the theory in a straitjacket and makes it super duper predictive. And this essentially follows from terms like here. So we see that the Higgs gauge interaction, F comes along for the ride with rho. So once F is set, the interactions between rho and A nu are fixed up to this factor of G. So indeed, we can put this in. I'll just rub this off and put this in. So in here, you get a term which corresponds essentially to the interaction between one Higgs boson, which is rho, and 2 gauge fields, which looks like essentially G times the mass of the gauge boson. And that's because MA squared was, you see from expanding this, G squared F squared. And so F is MA over G. So you can plug that in and look at the trilinear term between these two. You get a factor of 2, which cancels that factor of 2. You get a G squared F, and G squared F is the same as G MA. So if you have measured G, the strength of the gauge coupling, which you might have measured in some other way, and if you've measured MA, the mass of the gauge boson, then you've predicted the coupling to the Higgs boson. And that's exactly what happens at the LHC. It's exactly the same mechanism. Then also, looking at this part of the potential, suppose you had measured not only MA, the mass of the gauge boson, but also M rho, the mass of the Higgs boson, and G. Well, it turns out that the trilinear coupling, so we're expanding this out to third order, the trilinear coupling of the Higgs is actually 1 over root 2 G M rho squared over MA rho cubed. That's the trilinear, the cubic term. So if we've measured G M rho and MA, we've predicted the trilinear, and that's, so it's more complicated, we're going to do it in a second, but that's exactly what happens, for example, for the Higgs at the LHC. The standard model, if you truncate it at dimension 4 operators, not above, then once you've measured the Higgs mass, which we have, the W and Z masses, which we have, and the electroweak gauge couplings, which we have, we can actually predict the self-coupling of the Higgs. So we have a real target. Now, we can't measure it very well at the LHC. We'd really hopefully go to a future accelerator to do that. But it's completely pinned down in a straitjacket by the assumption of the symmetries and truncating the action at relevant interactions. Similarly, imagine we had coupled phi to some fermions. Okay, we'll do this and then we'll go on to the standard model. So suppose we had truncated, suppose that phi had, in this gauge theory, had some interactions with fermions. So for instance, imagine there were two Weyl fermions. I hope you're not getting sick of my use of Weyl fermions, but I find this better. So we call it psi A, which has something like charge Q under the U1 symmetry, and psi B, which has charge Q minus 1 under the U1 symmetry. Then it's impossible to write down a simple mass term. Something like phi A squared is ruled out, psi B, squared is ruled out, psi A, psi B is ruled out because of gauge symmetry. All of them are ruled out because of gauge symmetry. Then we would say that this theory, the terminology we use is we say that this theory is chiral because the gauge symmetries alone are forbidding a mass term for the fermions. If they weren't, we would say that the theory is vector-like. However, it doesn't forbid a term that looks like this. And you'll see where this is going. This is entirely analogous to the Higgs sector in the standard model, plus Hermitian conjugate, something like this. So here we said that phi had charge 1. The sum of the charges of psi A and psi B is minus 1. So this thing here is actually gauge invariant. If I do one of these local U1 transformations on this term here, it will remain unchanged. Okay, but recall that phi got a vacuum expectation value. It rolled out all the way to that local minimum of the scalar potential. And this means then that this Lagrangian in the vacuum becomes y over root 2 f plus rho psi A psi B. And so when rho is 0, we see that the mass of the fermion, so in the vacuum where rho is 0, we haven't oscillated that radial mode at all. In the vacuum, the mass of the fermion is just y f over root 2. Okay. Then this also means that the Yukawa, if we've measured the fermion mass, and we've indirectly measured F by measuring the gauge interaction G and MA, because MA was just GF, then F is MA over G. So then from here we can predict that the Yukawa interactions, this is an interaction. So I'll do this trilinear, the Feynman diagram for the trilinear here is just 3 Higgses interacting. The Yukawa interaction, this here, is y over 2. But we can rewrite that as G mf over ma. So if we've measured the fermion mass, and we've measured the vector boson mass, and we've measured the gauge coupling, we can actually predict the Yukawa interaction, the strength of interaction between the Higgs and the fermions. And so the point of all of this is to show, and we're going to do it in more detail in a second, but the point of all of this is to show that the hypothesis of the Higgs mechanism is the Higgs mechanism at play in any of these in the underlying scenario of spontaneous gauge symmetry breaking, then there's certain predictions which are completely non-negotiable. The symmetry puts a straitjacket around the theory, even in the broken phase, even when the symmetry is spontaneously broken, there's enough of it remaining, there's enough of its influence remaining to make certain predictions about the rest of the theory. And these are the predictions that we actually go and test in the standard model. When we say we're testing the Higgs mechanism at the LHC by measuring the Higgs couplings to fermions or to the vector bosons, for example, to ZZ or WW, we're really testing precisely this fact, that once we've measured a handful of other parameters, the final things to measure are completely predicted in terms of those parameters. So the Higgs coupling, the Higgs coupling to two gauge bosons is completely fixed in terms of the gauge boson mass and the gauge coupling. The Higgs trilinear coupling is completely fixed in terms of the gauge boson mass, the gauge coupling, and the Higgs mass. And the Yukawa couplings are completely fixed in terms of the gauge boson mass, the gauge coupling, and the fermion mass. And so if there were any deviation, those predictions are now made, they're set in stone. And if there were any deviation from those predictions that was observed at the LHC, it would mean something else is going on. It cannot be the standard model. And that's why it's so important to measure these interactions with as much precision as we can possibly muster, because it's a really big test of the standard model. Okay, and I'll just finish up. The next lecture will work through the actual Higgs sector, but I'll just finish up now by saying, pointing out that this theory was actually a little bit sick. When in the last lecture, when we discussed anomalies, I said that one way of seeing the anomaly is that because the path integral itself is not invariant under the symmetry transformations. But actually, the other way to see it is by doing calculating what I refer to as triangle diagrams. So there are diagrams that look like this, where we have some symmetry operation, symmetry current inserted here, and then a triangle diagram, and then, for instance, two gauge boson fields. But for a U1 theory, there are other diagrams that can also contribute. So we can have things like, gauge field, gauge field, gauge field. And each time you insert a gauge field, you get a factor of the charge of the fermion under that gauge symmetry. So if it was charge Q, you get a Q cubed in here. And if it's Q minus 1, you get a Q minus 1 cubed. And for the theory to not be anomalous, the way those triangle diagrams work is that if you add them all up, they have to vanish. And that essentially implies that the path integral will not change under the symmetry. There's a deep connection between these simple triangle diagrams and the variation of the path integral measure. And so, in this case, there's actually a problem, because here we have one Bell fermion of charge Q, another one of charge, minus Q minus 1. That should be minus Q minus 1. Minus Q minus 1. And so the anomaly does not vanish. So here you would have to have some additional matter, some additional fermions that are charged under the U1 symmetry that absorb this. And also you want in practice the anomaly to cancel when you have one insertion or with three insertions. So there's a very tight constraint on the theory, and it's sort of remarkable that the standard model is anomaly free, because when you write down typical dumb models like this, they will usually be anomalous. So this can be all of the fermion content when one is careful about things. Okay, so I think that should do us for this lecture, and then in the next lecture we will apply these ideas to the Higgs sector of the standard model. I'll finish there.